帮我把那个电牌关掉好了。给你。
我还有别的课啊，不是走数学。
还有什么？
填
它第二个关掉。
应该蛮难的。
填超越。
Okay. Let's look at e-learning system. As I mentioned before, there's going to be a quiz, a second quiz, 2 weeks from now. So please try to catch up the schedule. Today we will continue the introduction to VLSI. We are around here. Okay, as I mentioned before, when VLSI is proposed the first time, it's a simulation language. It's a model for discrete event simulation to verify that your digital circuit is correct logically. But after some time, they found that it can be also used as specification language for the logic sensing purpose. It means that it not can only simulate for your design to verify that, but also you can use that code for your design and try to translate it by using the translator. So logic sensing convert a subset of the VLSI language, not the whole set, no. Some of the statements cannot be synthesized. You have to be aware that. We'll mention that a few minutes later. Only a subset, but most of them can be translated into the next. For example, all the structural model can be translated. All the structural model can be synthesized to the next list because it's already a next list inherently. And it's one of the major breakthroughs in designing logic chip in the last actually 30 or even 40 years. Most chips nowadays are designed using at least some logic senses. Maybe some high-speed circuit purpose you want to have for custom design. But most of the chips are designed with the hardware discrete language and using logic sensing to translate it into the circuit. There are many logic sensing tools in the market, but they are difficult and complicated to write well. And in the limited market, the commercial product is around 10K to 10 to 100K, so it's quite expensive actually. But in Taiwan, the university can try to use them free actually by the student. It's supported by the government. There are some major vendors like Census, Cadence, Simplicity, example, and there's also some academic tools. We have already covered that last week. For logic sensing, there are 2 stages actually. There are 2 phases. The first one is translation of VLSI code, the source code, to a next list. Okay. This is the first step. In the first step, you translate it into the next list using logic gate, basic logic gate, using like flip-flop and latch, how they are connected. And the second step is critical. It tries to optimize the next list produced by the first phase to improve the speed and area. Typically, the user can give some instruction, can give some constraint. I want that circuit to be very, very fast. There should be operate in 1 nanosecond, in one clock cycle, 1 nanosecond. Then the software try to meet your constraint, try to give you a very high speed circuit. If it fails, then it will tell you that no, there's no way I can come up with a 1 nanosecond circuit. Then you probably have to maybe increase the constraint from 1 nanosecond to 1.2 nanosecond, something like that, and try to hopefully you can get the circuit produced by the software. You can also define chip area. I want that to be very inexpensive. Hopefully, chip area should be as small as possible. Then you can give the constraint. It should be within like 0.5 centimeter square. Then the software try to meet the requirement. Maybe the circuit is low, but it will try to give you a small chip area for that circuit design. So this is a very critical part of the process. There are all kinds of algorithms, many algorithms, and very complicated algorithms. They can try to give you a better circuit in the second phase. For example, you have already learned column map in digital logic design, right? Column map. You can try to minimize your combinatorial circuit by trying to simplify the Boolean function, trying to reduce the logic gate, so on and so forth. That's part of the optimization. Okay? And the net list optimization is a critical enabling technology. Nowadays, very, very important in this area. It takes a slow or large net list and transform it into one that implements the same functional more cheaply, either in terms of timing or in terms of chip area. And there are many kinds of techniques to optimize that circuit design. For example, constant propagation. For example, common sub-equation elimination, like function factoring. We're not going to give to try to look into the detail. Just give you some name. Okay, we don't have time to cover that kind of algorithm for optimization. It's a time-consuming operation. Can take hours for large chip, but the end product, the end design will give you very, very good either performance or very small chip area. In very long, we try to translate it into the circuit, part of the language easy to translate, especially structural model. For structural model, with primitive, it's already a net list. So actually, when you translate it into the circuit, translator, they are exactly the same net list, but with a maybe more efficient form. And also for continuous assignment, it's a high-level description, but in the library, you might have some circuit that can replace the statement in the continuous assignment. For example, addition. For addition, actually, the translator and the library, they can provide you with the adder circuit. Equation turn into little data pad, like adder, subtractor, so on and so forth. And the more challenging part actually is the behavioral model. Behavior statement is higher level description, so it will be more difficult to translate it into the real circuit. As I mentioned, structural model actually can be translated. Every structural model, all the structural model statement can be translated, no problem. can be synthesized, not just generated, but it can be synthesized into circuit, no problem. For behavioral model, it depends. It depends. Actually, even for different sensor tool, they might support different scope of behavior model. For behavioral statement, it depends on sensitivity list, like old block, like initial block. Only when they have reasonable interpretation of the conventional circuit, conventional logic, edge, or level sensitive latch. Only when they can be interpreted logically as a circuit block, then they typically can be synthesized. Otherwise, some circuit with behavior model cannot be synthesized. For example, like while loop. So while statement is a legal value statement, but typically most of the synthesize tool cannot synthesize for while statement. Because while statement means you're trying to check some condition and then you're doing the follow statement sequence. But it does not correspond very well to the real circuit. Or for again, this kind of statement cannot be synthesized. Although it can be written in behavior model, but it cannot be synthesized into a circuit. Although actually there are very few companies try to support that with hardware design, but don't rely on that. You should assume that they cannot be synthesized. Only when they have reasonable interpretation of conventional logic, edge, or level sensitive latch, then they can be synthesized. Block sensitive to both edge of the clock, change on unrelated signal, changing sensitivity list, so on and so forth, cannot be synthesized. Typically, they cannot be synthesized, including both edge. Although, yes, you can design that kind of circuit for both edge, but in synthesizer tool, they don't support it. And also, change on unrelated signal, they cannot be supported. And changing sensitivity also cannot be synthesized. For UDP, user-defined primitive, you write the UDP using truth table. We mentioned that before. Give the truth table for user-defined primitive, such that they can be simulated very, very fast. Some special UDP cannot be translated. Okay, so if you are not sure, try to avoid those statements that probably cannot be synthesized. Simply use those statements that can be synthesized for sure. That would be safer. I'll give you some example. First one, initial block cannot be synthesized. Initial block. Because for initial block, it means that we are going to execute the sequence of statement in the block just once, right? For all block, they keep executing the statement in the block, keep doing that. So all block correspond very well to hardware circuit. For hardware circuit, as long as you have some power supply, they can be running. Okay? Until you turn on the power, they keep running, they keep working, the typical hardware operation. But for initial block, you only execute once in the code. So that's not a typical hardware behavior. However, initial block can be used for verification. It can be used to set up initial state or describe finance test bench stimuli. You can define your stimuli using initial graph. We gave some example before, right? We look at initial graph. Okay, here. This is the initial graph. We try to provide input pattern, input data, and after some time delay, some signal change value, so forth. So this is a typical statement to provide input data and only once. It's not going to continue executing the statement because this is not a always run. So it cannot be synthesized, but you can use that for your test bench. They don't have obvious hardware component, okay? Corresponding hardware component. Delay also cannot be synthesized. When you see this kind of value, it means that you have 5 time unit delay. However, although you can simulate for the delay, for sensing, circuit sensing, they ignore that. It may be in the very low source, but they are simply ignored when you try to translate into a circuit. Why is that? Because you don't know real delay after you synthesize to the circuit, right? The circuit depends on many issues, many factors, like the wire length, like where you put your circuit in the layout. It depends on your final layout. You simply don't know what is the real delay when you write the code. Not yet, you don't know yet. So for delay, just for simulation, it's not translated into a circuit. A variety of other obscure limiting features. If you don't, as I said, if you're not sure, try to avoid using that kind of statement. In general, things heavily depend on discrete event simulation, semantic, loss statement typically cannot be synthesized. Any questions? Register inference. In Verilog code, you can declare red, right? Red is the data type. However, as I mentioned before, although some variable is the red data type, there's no real free-form or latch when you translate it into the circuit. Example, in the multiplexer example, here, F is the red, you declare the red data type. But the real circuit, F has no latch, has no flip-flop. F is simply the output of a conventional circuit. So red does not exactly correspond to the latch. The reason why it's declared red is for simulation purpose, F will remain the previous value. Remember, you keep the previous value unless you assign a new value, unless there's some input data change. Then you do evaluation and then assign to F. Otherwise, F simply keeps the previous value, the last value. That's for simulation. For real circuit, well, there's no latch at all, actually. So red does not correspond the latch or free-form. But we mentioned that if F is on the left-hand side, there's a statement, something like F equal in some Boolean function, then yes, f has to be declared red. Okay, has to be declared red. Rule: combinational if output all depend exclusively on sensitivity list. Although the variable is red, but it's going to be a conventional circuit. Conventional output if they depend on your sensitivity list exclusively. If that's exactly the output of a conventional circuit. But it's going to be sequential. If output may also depend on previous value, because there's a timing concept. If you depend on previous value, there must be some kind of latch or register or flip-flop to remember the value, to store the value. Any question? Give me some, look at some example. For this circuit, Y is red, okay? You declare that. And all A or B or select. If select is true, it's 1, then B assigned to Y. Otherwise, says 0, A assigned to Y. So that's typical two-input multiplexer. And as I said, if Y appear on the left-hand side of the assignment, then it's going to be declared, it has to be declared red, because it will remember the previous value for simulation. In terms of hardware, no, there's no flip-flop. Because it exclusively depends on your sensitivity, right? Sensitive to change on all the variable is read in here. However, in this case, Q declared red, and it indeed has a latch. Indeed has a storage element in the circuit. Q only assigned when clock is 1. Alt A, D of clock, D is the input, clock is the clock signal. If clock is asserted, then E assigned to Q. That's a D flip-flop, right? The typical D flip-flop circuit. In this kind of circuit, yes, there's a latch, there's a flip-flop, the storage component in the circuit. Another example for register in the code. When you write a regular code, a common mistake is not completely specifying a case statement. Okay, case statement is very useful for your regular code, but if you are not careful, it might influence that there's a latch in the circuit when you do the synthesis. For example, alt A or B, okay? When A or B change, we do the following, is a case statement. Case A, B is concatenate, meaning it becomes 2-bit value. 2-bit value, binary value, 0, 0, F equals 0. 0 assigned to F. If AB is 0, 1, you assign 1 to F. If AB is 1, 0, you assign 1 to F, then A case. You saw that it's going to be a combinatorial circuit, but actually, no. After you do the circuit synthesis, it will give you sequential circuit. Why? Why that? Because the synthesizer saw that this code implies that there is a latch Why is that? The reason is that you did not assign F value when A, B is 1, 1. You did not cover all the cases, okay? One last case is omitted. And the tool assumes that, okay, you did not give a value, then it implies that it's going to remember the old value. So there's a register flip-flop, there's a latch in your circuit. Let me repeat it. The tool can do register inference, although there's no reg in your code. Because in this case, statement here, you cover 0, 0, 0, 1, and 1, 0, 3 cases. However, you forgot to include 1, 1. If there's no 1, 1 case, it assumes that, the tool assumes that your circuit will keep the old value. So there must be a flip-flop or latch included in your circuit. You produce a circuit that has a latch, which probably is wrong, because in your mind, you might think that, well, 1, 1 is not a case I'm concerned about. There's no way there will be 1, 1 signal value in your circuit. However, the tool will assume that if you don't cover the other cases, then there must be some circuit that will remember the old value and keep the old value. So you have to be careful about that. Any question? The best way to do that is give a default. If these are 3 cases you are concerned about, and for the other cases, you assume that it won't happen, but still, you have to give a default value. Default value is 0. Then you will get a combinatorial circuit, which is quite wrong. In other words, you have to cover all the cases. Don't omit some of the cases. The solution always has a default case. Besides that, latch and flip-flop often have reset signal, reset input. So when you design your circuit, try to have reset. Maybe reset is not needed in some cases, but most of the time, most of the chip, most of the circuit system should have a reset signal, because when you turn on the power, when you start a circuit, all the flip-flop, all the register should have an initial state, should have an initial value. Try to avoid random data when you turn on the power. So this reset signal can be synchronous or asynchronous. What does that mean? This is a D flip-flop. Flip-flop, tune output, and there's a clock in. If there's no reset signal, then in the beginning, you don't know the value for Q. In the beginning, you don't know. But if there's a reset signal, then the initial value is going to be 0. Reset, or you can also set it to 1. Fine. It's doable. It can be designed. But try to have reset signal every time, such that the machine, the circuit, will enter a fixed state, a determined state at the beginning. That will be easier for your design, to avoid errors. But there are 2 kinds of reset signal. One is synchronous, the other one is asynchronous. In this case, example, always at positive edge clock or port 8 reset. If reset, 0 assigned to Q. Otherwise, D assigned to Q. What that circuit is? What is this circuit? It's a D flip-flop. But there are different versions of D flip-flop. If we write the statement like this, port 8 clock or port 8 reset. It means that whenever clock goes from low to high, or when reset signal goes from low to high, then we check. If reset is 1, 0 will assign to Q, initialize. Otherwise, the input will enter the flip-flop and assign to Q. These are asynchronous reset. It means that when you assert reset, it will force the Q output to be 0 immediately after some delay, after a small delay. Q will be set to 0. You don't have to wait until clock signal goes from low to high. You don't have to wait the clock signal. When you assert reset signal, it will do the resetting immediately. In the circuit, when you assert reset signal, you still have to wait until clock from low to high. Then it's a synchronous D flip-flop. Synchronous reset D flip-flop. Okay, let me repeat it. When you press the reset button, then you get Q output 0 immediately. You don't have to wait until the clock signal goes to high. Meaning this is asynchronous reset signal, not a synchronous. For synchronous reset signal, you have to wait until clock goes to high. Try to synchronize with the clock signal. That synchronous D flip-flop. For asynchronous D flip-flop, with asynchronous reset signal, it will do resetting right away. So in this case, it's asynchronous. Why? When reset port 8 goes high, it will do the checking. Checking that, yes, if reset signal is 1 now, Q will get 0. Otherwise, it's because of the clock signal goes from low to high, then D will assign to Q. So this is an asynchronous reset flip-flop. Any question? Because the Verilog is proposed as a simulation language, so they try to convert it, right? They try to also use it as a spec language. So there are some possible source of conflict. Since it ignores delay, okay, I mentioned that already, right? You don't know the real delay actually, so it doesn't make sense to give a delay for your circuit before you get a real layout. But simulation, yes, you can have delay. You try to wait for 10 time unit and then do the following. Simulator model X implicitly, but since it does not, X means don't care or don't know. But in your circuit, there might be some signal. There's no don't care signal. Okay? Behavior resulting from sheer variable like behavior or red is not sensor. Well, it means that you have to be careful when you have share variable statement. You have the variable A, and A is actually some signal from the other block. The new value of A may be seen by others at positive clock statement in simulation, but it's never solved in synthesis. For simulation, it's fine, but for synthesis, try to avoid this kind of circuit. The A is not part of the sensitive list, although it can be simulated, but try to avoid that. The variable is not covered in sensitive list. All right, just summary for this unit. System described hierarchically. You can define many kinds of module, and then you can call module. For instance, in many places, module with interfaces. Module contains instances of primitive and or other module. So it's that nested procedure call, right? A module contains initial and OS block. It's a typical block in your module. Remember that OS block can be synthesized, but initial block cannot be synthesized. Based on discrete event simulation or semantic, that's how we interpret the very code simulated. It's going to be translated into concurrent processing with sensitivity list for the simulation. And the simulation scheduler will run part of this processing in response to change. As I mentioned before, you're going to have an event queue, and the type of simulation advance to the next time point and run the event or simulate for the event. Keep doing that until there's no more event in the queue. And as I mentioned, although it provides switch level primitive, people actually don't use it. It's not very useful. But for gate level primitive, then they are useful. It can be for Boolean logic gate. And it can also have user-defined primitive defined by yourself. Gate and sequential element defined with truth table. That can be run much faster if you have user-defined primitive writing the truth table. Continuous assignment is very useful statement. It can model conventional logic with equation. And initial and OS block. Very common in your visual code. It gives the procedural modeling of behavior, the typical behavior model. And net or while for modeling interconnection. The while connection, you declare that they are net or while. So it cannot remember the state, it cannot remember the value. Keep just propagate the signal. Value set continuously. And red for behavioral modeling. We have exactly like memory for imperative modeling, but it does not always correspond to real memory component, real storage component in the synthesized named list that I mentioned before. That's for simulation. Blocking versus non-blocking assignment. Blocking behave like normal C-like assignment. When you complete that assignment, and then the next one, and then the next one sequentially. For non-blocking assignment, they evaluate on the right-hand side, and then assign to the left-hand side. Okay, it's non-blocking assignment, like synchronous circuit behavior. Event-driven simulation, as I said, event queue containing things to be do, things to do at particular simulation time, at the time of simulation advance. evaluate and update event. And each event can trigger more events to the queue for future simulation. Compile code event-driven simulation for speed. Is a discrete event simulation, not continuous event. So it can be simulated very efficiently. For logic sensing, very useful process. You can translate various code, including structural and behavioral. For structural, they all can be translated. For behavior model, it depends. Depends on what kind of statement. Some are supported, some are not supported for the translation to native. Rational inference mentioned it could infer some register implicitly, even some lag implicitly if you don't write your statement clearly. And logic sense optimization, we try to optimize the circuit either very fast or very small. Just keep switch levels in our model. They are not useful. And for delay, the simultaneous circuit will delay actually just for simulation, but it does not really correspond to real circuit delay, so it does not improve confidence enough. It's hard to get timing model accurate enough. Okay, and never sure you are if you have simulated the worst case. The delay is only for simulation. For real estimation of the delay, try to use static timing analysis. In the tool, there is some kind of static timing analysis tool to help you to estimate the real delay for your real code, providing some specific library. In Verilog compared to VHDL, they are all high-level, highly distributed languages. VHDL is likely wider scope, cover more stuff. System level modeling, they pose even more discrete machinery. It's very better behave, but from efficiency point of view, actually Verilog is better. It's simpler and it's better for efficiency. But for VHDL, it probably can avoid some mistake, some error by the users. And it's harder to simulate quickly. And okay, so just give some idea. There's a different language, but actually they look similar. Although Verilog is deeply for language because they don't know the synthesis in the beginning when it's proposed. Non-deterministic, often weird behavior. So using Verilog, you probably need some experience. More experience will help you design better or more efficient circuit. But still, Verilog is widely used because it solves a problem and it's very efficient, it's very simple compared to VHDL. With simulation speed, okay? And the way we have subset language. Okay. It's a reasonable spec language for logic synthesis. Okay, so we still use Verilog a lot, especially in Taiwan. That's the language we use. Okay, that's the end of the Verilog introduction. Any question? Last time I mentioned that we are going to the teaching lab for doing some exercise, but not this week. I'm going to postpone it to next week. I'm trying to cover more stuff such that you can go to lab and do some real design, like Ada or something like that. Okay, any questions? Okay, let's take a break. please download the lecture file for the other unit.